Okay, perfect. All right. Hi, everyone. My name is Neekon, and today I'll be talking about continuous LWE and our results that continuous LWE is as hard as LWE. And this is joint work with Parna and my advisor, Vinod at MIT. So the brief outline of what I'll talk about today, I'll talk very briefly about learning with errors that I'm sure most of us are familiar with. I'll talk about a continuous analog that was recently defined called continuous learning with errors, or CLWE. I'll talk about some of the applications of CLWE and why the problem is interesting. And lastly, I'll talk about our result, reducing LWE to CLWE, and I'll mention some of the applications. Okay, so LWE is something I'm sure many of you are familiar with, so I'll go pretty quickly, but if anything is confusing, of course, feel free to stop me. So let Z sub q denote integers mod q. N of mu sigma squared will denote the univariate Gaussian distribution with mean mu and standard deviation sigma. The decisional LWE assumption says that if we have a secret vector S uniformly randomly drawn from ZQ to the N, and we take, let's say, M samples, where we have each AI drawn uniformly at random from ZQ to the N, and we have noise EI from a univariate Gaussian with mean 0 and standard deviation sigma, we have that the samples AI, along with noisy inner products of AI with the fixed secret S, taken mod Q, should be indistinguishable from AI along with uniformly random real numbers between 0 and Q. So just one way to formulate the standard decisional LWE assumption. Okay, so why care about LWE? Certainly many reasons. One reason we care about it is that they're worst case to average case reductions for LWE. There are both classical and quantum ones, although the classical reductions have some worse parameters, but the reductions still do exist. And so now, LWE is fundamentally an average case problem. So now to show average case hardness of LWE, it suffices to show worst case hardness of certain lattice problems. You can also build lots of cryptographic primitives from learning with errors, such as one-way functions, public key encryption, and lots more. And in fact, these are secure in a post-quantum setting as well. And you can, in fact, even build a quantum cryptography. So like not just in a post-quantum world, but truly quantum cryptography, assuming the hardness of LWE, such as classically verifying quantum computation and producing certifiable randomness from an untrusted quantum source. Okay, let me switch gears a bit and talk about the continuous variant of LWE defined by Bruna-Regev-Song-Tang. So on the left is just I've reproduced what I've said about LWE, just so you can compare. So for CLWE, let S to the n-1 denote the unit sphere in Rn. So just the set of all unit vectors in dimension n, which you could think of as an n-1 dimensional sphere. So our secret is going to be sampled uniformly at random from this unit sphere. Each sample is now going to be drawn from a multivariate Gaussian, where the mean is the all zeros vector in R to the n, and the covariance matrix is the identity. And another way to think of this distribution is that you have n coordinates, each of which is independently a univariate standard Gaussian. So you can think of each coordinate as being a Gaussian with mean 0 and variance 1, and just have independent copies of it in dimension n. The noise is once again going to be from a univariate Gaussian. I'll just give the parameter a different name than LWE just so we could compare the two. And once again, the assumption is that if you take these samples AI and you look at noisy inner products, it should be computationally indistinguishable from AI along with uniform random real numbers, now mod 1. So let's just take a second to compare these two. So I've certainly introduced some new parameters, this beta and this gamma. And let me try to give some intuition as to how to think of these parameters. So I urge you to think of beta as really being like a noise to signal ratio, because we're taking things mod 1 and we're adding some noise of width beta to it. So think of beta as exactly how much noise you're adding to the signal. And just an analogy with LWE, the noise to signal ratio in LWE is going to be sigma over Q. So I urge you to think of beta as being roughly this quantity, and later I'll make this a little bit more precise. But certainly think of beta less than 1, maybe like 1 over a polynomial in n, for example. But in analogy to LWE, think of it as roughly sigma over Q. What about this parameter gamma? Like why even have a parameter gamma? There isn't really a parameter gamma in LWE. The point is a little bit of a syntactic one, which is that in CLWE, our secret here is a unit vector. Whereas in LWE, it's certainly not. It's drawn uniformly at random from ZQ to the n. So you could think of gamma as really absorbing the norm, like the magnitude of the norm of this secret vector. And certainly in dimension n, think of it as being at least root n. Okay, so now just to get a little bit of a geometric understanding of what CLWE is. So here I've plotted some CLWE samples in dimension 2. So in the xy plane, we're going to have samples from a 2-dimensional standard Gaussian. And the color is represented by the second component of the CLWE samples, these noisy inner products. So there, and mod 1 is indicated by the color in the bar here. In this case, the secret vector is straight up and to the right. And one thing you might notice is that you have bands of the same color roughly in perpendicular slices to the secret vector S. And the reason for that is that these second components really only care about your projection onto this vector S. So that's why you see the structure of like hyperplanes, in this case, like lines in dimension 2, perpendicular to the secret S. Are there any questions about this distribution? I'll certainly be talking about this a lot, so.
It's a question, because this is just my bad intuition about continuous things. So is there a regime where it's clear that the problem is statistically hard? Like with LWE, if I don't have enough samples, then it's statistically hard. Can you say something analogous here?
Yeah, probably like similar low samples should be statistically hard. Certainly if your noise is really big, it'll be statistically hard.
Can you repeat what was the reason for the gamma parameter again?
Right, yeah, okay. So the point of gamma is that in LWE, there's the secret might have arbitrary norm. It'll be like at least root n, maybe like q root n roughly. But in CLWE, our secret vector is drawn from the unit sphere. So it always has norm 1. So you could think of gamma as essentially like taking account for the fact that in LWE, there's some norm that's being hidden here because the secret is a unit vector.
So you just say now I'm gonna look at that from the unit sphere. Sorry.
Like you can think of it as saying, okay, exactly. You could totally think of this instead of saying the secret is from some fixed ball of a given radius gamma, instead of having a unit sphere and then scaling by gamma.
So I'm just pattern matching here, but you said gamma should be larger than square root n, and in Regev's reduction, somehow sigma is supposed to be greater than square root n, and I'm just guessing that those are probably the same thing, except if that's actually true or not.
Let me think. Well, certainly the root n comes from the fact that like we're in dimension n, so things definitely have L2 norm at least root n if you have non-zero coordinates. If you mean in terms of the reductions from like.
Yeah, so try to think of like gamma equals root n, meaning like S is actually sampled from like a standard Gaussian as opposed to from this.
Yeah, that's how I think of it. And this will come up later, but imagine LWE where the secrets are drawn from binary distribution. In that case, the secrets really have norm roughly root n or exactly root n, depending on your setting. And so that's one way to think of this as well.
But why is it important to make the secret has larger norm, square root of n norm? Because one is in mod Q, the other is mod 1. I don't know how to compare these things.
Well, I guess, so just in comparing, you could certainly divide by Q here. Now we're really just comparing things mod 1, sort of apples to apples. But if the gamma here is like 1, so this problem becomes actually easy. It turns out there's a problem, there's an algorithm for this problem running in time 2 to the gamma squared, roughly. Maybe it's from some poly n factors or logs somewhere.
That's very analogous with LWE.
Yes.
Yeah.
Right.
Running into the sigma squared. Yeah.
Exactly.
but somehow gamma is like sigma and beta is somehow like sigma over Q.
Yeah, we'll later get the connections and sort of.
What was the comment again?
The comment, so yeah, no, we're saying that you could think of sigma as really being this gamma because the best algorithms are 2 to the sigma squared. Here it's 2 to the gamma squared. Like maybe that's one way to think of this analogy.
So sure. I mean, sigma and beta are clearly analogous. But,
Yeah.
And gamma is really like the norm of the secret. That's exactly what it is.
Yeah, but somehow this pattern matching is like remarkably.
Sorry.
Somehow pattern matching gamma with sigma is like a remarkably successful way to think about this.
I think that's exactly.
Yeah, yes. So we'll see later how to match parameters, but certainly, you know, it's not like a 100% clean mapping. So maybe there's some settings where you can think of it as sigma, and some as Riemann.
What's an equation for beta? Like how small the definition?
Yeah, so in fact, certainly if beta is 0, this is actually solvable with LLL. And even if it's exponentially small, it's also, you can use LLL to solve this.
So should I just think about the right-hand side is the left-hand side divided by Q then?
Yeah, but you know, these samples are from a different distribution. Like your secret is from a unit sphere, and your samples are from a Gaussian distribution.
Even in LWE, we can work with entropic state.
Yes, totally.
Yeah, so that part seems to be less important, less crucial, maybe still important, but I see some bigger differences the AIs.
Sure. And you know, just speaking ahead, you know, we give a reduction between the two problems. So you're right, they aren't too different, ultimately. But
Oh, so the AIs are sort of Gaussian now. Okay.
There's a question here for you, Matt. Why can't you divide the second component entirely by gamma, right? And that would really sort of seem to make things, you know, like one parameter, which is, the error will divide by gamma. But the point is that the mod 1 will become mod 1 over gamma as well. So gamma somehow relates to the most significant bits, the Q or the mod 1 here, whereas the beta relates to the least significant bits, which is the analogous thing is sigma.
Is there LWE variant of this?
You could make up one.
yeah, I don't think it's been defined formally, but certainly it's, I think that makes sense. Yeah. Okay, let me just move forward. So, all right. So yeah, what do we know about CLWE? One thing we know is that there's a quantum reduction from worst case lattice problems for gamma at least root n. And one might say, okay, great, but you know, for LWE, we also know a classical reduction. So you know, what's the advantage of looking at this problem CLWE over LWE? You know, fair enough, fine. From CLWE, we actually know how to build a public key encryption. But, you know, once again, like from LWE, we know how to build lots more cryptography. So you know, what's really the point of CLWE? Like why give this definition at all? The main point that I'll try to convey through the rest of this talk is that CLWE has connections to natural problems in statistical learning or machine learning. And I'll give some examples of this throughout, but this is really the reason why CLWE is fundamentally an interesting problem, in my opinion. And some of you may be familiar with problems like planted clique and the whole web of reductions that exists from planted clique to various other problems in high dimensional statistics. One can ask, maybe does the same thing hold for CLWE? And I'll try to give some like very beginnings of a possible set of reductions between problems in statistics and CLWE. I should say before moving on that we do know some learning hardness from LWE, but sort of that's in the Boolean setting, and I urge you to think of the CLWE type statements as being much more naturally close to problems you'd consider in machine learning or high dimensional statistics. Okay, so let me talk about the first example. First example is that CLWE implies hardness of learning a single periodic neuron. Neuron here in the sense of neural network, and periodic here because the activation function we consider is going to be a periodic function. So in general, you know, it's known that it's NP hard to learn neural networks in the worst case, but sort of in learning tasks, you really want average case statements. You know, your input probably comes from some distribution, and you'd want to argue average case hardness for these problems. So let me give one example problem. Suppose we have some function f of x, which is going to be the inner product of some secret with x, and then apply cosine to it with some scaling. Or your inputs are not from some distribution. They're from the multivariate Gaussian. So this is really an average case problem now. And in fact, the function is average case too. We define this secret from a unit sphere in Rn. The point is that this is actually a very simple neural network right here. Why is it a neural network? It's a neural network because you take your input x, you apply some linear function to it, namely the inner product with s, and then you apply some nonlinear activation function to it. In this case, cosine of something times it. And nonetheless, even for this very simple neural network, there's a reduction from CLWE to learning noisy samples from this neural network. In other words, the CLWE assumption implies that it's hard to learn functions given noisy samples, noisy labeled samples. In fact, the reduction is straightforward enough that I can hopefully fit it in the rest of this slide. The proof is a direct reduction from CLWE, where you apply cosine to the second components. So what happens? You take cosine of 2 pi times this noisy inner product, mod 1, and a few things happen. The first thing that happens is that this mod 1 now completely goes away, because that just corresponds to adding integer multiples of 2 pi to cosine, which has no effect on the cosine. And the second is that we can bring out our noise EI into some different noise EI prime that's going to be not too much bigger than EI, just because cosine is nice and Lipschitz and doesn't have a large derivative. But this is exactly a noisy sample from this function f sub s. So just by applying cosine, we've mapped the problem of CLWE to this learning task from a very simple neural network. And so CLWE implies hardness of learning this neural network in an average case setting. You have average inputs, and your function is also average case. Okay, I want to move to a different example, which says that CLWE can allow an adversary to plant undetectable backdoors in certain models. And so in general, in machine learning, it turns out that linear classifiers put on top of random features or random functions of your input data tend to be reasonably expressive and of some nice properties. In other words, you take your input data, you apply some random functions to them, and then you train some linear classifier on top of these random functions. These have some nice properties, it turns out. And one set of random features that people consider are random Fourier features. And don't worry too much about the math or the exact structure of these functions. I'm not going to refer to them later on in the talk. But the important thing to note is that these random functions are defined by the randomness given by this WI here and this phase BI. And this WI is from a standard Gaussian, and the BI is some phase. It turns out that for assuming the hardness of CLWE, an adversary can undetectably change the distribution of WI, and as a result of that change, it can plant backdoors in the model. And what do I mean by a backdoor in the model? I mean that if you let the adversary train your model, if you replace this WI with some backdoored randomness, the adversary can give you labeled examples with flipped classifications, for example, with only a small perturbation in the input. And just for the sake of time, I'm not going to get into the proof of how this is done, but it's just changing the randomness of WI into something that is indistinguishable computationally, assuming the hardness of CLWE. Let me move to my last example, and the one I want to focus most on is that CLWE implies hardness of learning mixtures of Gaussians. And so what do I mean by a mixture of Gaussians? So in general, a mixture of Gaussians is a distribution D whose density function can be written as a convex combination of multivariate Gaussian distributions. You could equivalently think of this as saying with every time you want to take a sample from D, with probability WI, you choose component I. And once you choose component I, you sample from multivariate Gaussian with mean mu I and covariance matrix sigma I. Just to get some pictorial intuition, in dimension 1, you could think of a density function of a mixture looking like this. The blue densities are the densities of each component, say weighted. And the red is the overall combination of these density functions. And mixtures of Gaussians are sort of a natural way to model things in science, in nature, and certainly in machine learning. And the natural task is, given samples from such a distribution, try to estimate all the parameters of this mixture of Gaussians. In other words, given sample access to this distribution D, estimate Wi, mu I, and sigma I for all I. That's a natural task. It turns out one can even define a weaker goal called density estimation, which is essentially an improper learning version of this, which says given ample sample access, output some distribution. It doesn't have to be a mixture of Gaussians, but some distribution that approximates the mixture of Gaussians. And you output the distribution in terms of a density function. So you output some candidate density function that's going to look close to the original density function. That's the mixture of Gaussians. And why do I say this is a weaker goal? I say it's a weaker goal because certainly if you can estimate the parameters, you can plug in those parameters and that instantly gives you a candidate density function. And it's in fact weaker in a stronger sense in that there are information theoretic separations between these two tasks in terms of sample complexity. Okay, so how is this at all related to CLWE? It turns out that CLWE implies hardness of learning mixtures of Gaussians, even this easier task of density estimation. Let me try to give some intuition for why this is true. So on the left here, we have our CLWE plot from before. But let's say my favorite color is red, and I want to look only at the red samples here. We'll get something that looks roughly like this. This distribution has a name. It's called the Homogeneous CLWE distribution. And that's called the homogeneous version because I'm conditioning the samples AI on the fact that the noisy inner products are 0 mod 1. Because the color being red exactly means that mod 1, the second component, is 0. And so if you condition your samples based on that condition, you're going to get exactly a picture like this. And just to get a sense of some of the geometry here, the separation between each of these slices or each of these pancakes, sort of in higher dimension, there's going to be a roughly 1 over gamma gap between each of these slices. And the width of each of these bands in itself is roughly beta over gamma. But the main point here is that this itself is a mixture of Gaussian distributions. Like each of these little slices is a Gaussian distribution, or your covariance matrix is squashed in the direction of the secret vector. And the means are going to be equally spaced out on the line generated by the secret vector S. So like each of these little components here is itself a Gaussian distribution. And another point I want to make here is how many components are there in this Gaussian distribution, in this Gaussian mixture? Well, because the gap between each of these Gaussian pancakes is roughly 1 over gamma, and because most of the mass of a Gaussian is sort of contained very close to the origin, there are going to be roughly O of gamma components that contains almost all of your mass of the Gaussian. So think of this as a mixture of Gaussians with roughly gamma components. And just to talk a little bit more formally, the decisional hCLWE problem or homogeneous CLWE problem is to distinguish this distribution here from just a standard Gaussian. And to you, maybe that sounds like an easy problem. Like, well, there are stripes here. Clearly, a standard Gaussian doesn't. Why is this a hard problem?
Distribution again.
Sure. So you can think of it as conditioning the CLWE distribution on the second component being 0 mod 1.
Being 0 mod 1. Okay.
So like roughly gamma times the inner product of the sample with S is going to be an integer, roughly. And indeed, we'll see that there's a reduction between CLWE and the homogeneous version of CLWE by rejection sampling. Just looking at that. Right, so there's the decisional problem is just to distinguish this from one standard Gaussian, or yeah, from samples from a standard Gaussian. And why is this hard? Okay, so one of these is a standard Gaussian. One of them is hCLWE. Can any of y'all tell me which is which?
Yep.
So wait, which one is which?
Left is CLWE.
Exactly. So the left one is hCLWE because for a split second in time there, you could see the discrete structure of hCLWE. Whereas in, yes, exactly. Whereas in the standard Gaussian, there's no discrete structure at all. And so the point is you have to look exactly at the right direction to notice this discreteness. And especially in higher dimension, when there are exponentially many directions you're going to have to look at, how do you find the right one that lets you see this discrete structure? That's the intuition as to why this problem is hard. And just going back to CLWE, as I alluded to earlier, there's a reduction from CLWE to hCLWE just by rejection sampling carefully. You take components, you look at the second component. If it's close to 0 mod 1, you keep it with some probability. And if you reason about this in the right way, you get a reduction. And because the homogeneous CLWE distribution is itself a mixture of Gaussians, there's a reduction from this decision problem, hCLWE, to even density estimation, it turns out, for mixtures of Gaussians. So what does the second statement mean? I'm just saying, if you have an algorithm that gives you a density estimate for mixtures of Gaussians, you can use such an algorithm to distinguish between the homogeneous CLWE distribution and the standard Gaussian distribution. In other words, you could perform some statistical tests on this density estimate that you get that allows you to distinguish between these two cases. And combining these two facts, just directly composing these reductions, we have a reduction from CLWE to learning mixtures of Gaussians. And I just want to highlight again that the number of Gaussian components is going to be roughly O of gamma. And gamma, as I sort of alluded to in the beginning of the talk, you should think of it as the norm of the secret vector. So roughly the number of components in your mixture is roughly going to be the norm of your secret vector that you start with, just for the sake of intuition. Okay, so let's take a little bit of a step back in comparing LWE and CLWE. So we know that LWE is hard under even classical worst case lattice assumptions, and you can build lots of cryptography from LWE. CLWE, we know it's hard under quantum worst case lattice assumptions. In other words, there's a quantum reduction. And I've just shown some examples that CLWE has natural connections to problem in statistics and machine learning. Someone can ask, can we show classical reduction from worst case lattice problems to CLWE? Or, more generally, LWE has been studied for a while now. Can we generically apply results we know from LWE, like tools or hardness, and can we generically port them over to CLWE? And the answer to both these questions we show is yes. Specifically, we show a classical reduction from worst case lattice problems to CLWE. And we do this by first using the fact that there's a classical reduction from worst case problems to LWE, and then by giving a classical reduction from LWE to CLWE. And composing these two gives a classical reduction from worst case lattice problems to CLWE. Okay, how do we show a classical reduction from LWE to CLWE? The first main step, as I alluded to a little bit earlier, is that we use secret key leakage resilience results for LWE to reduce to a binary secret version of LWE with some slight increase in the dimension and some other loss in parameters. So we first do that. And then we show that if you start with LWE, where all of your secrets have some fixed and ideally small norm R, then you can reduce LWE to CLWE with the following parameter dependencies. So this gamma parameter in CLWE will be roughly the norm of the LWE secrets that you started with. So this sort of justifies what I mentioned earlier, when I defined CLWE. And also this beta parameter is up to constant factors going to exactly be the inverse of the signal to noise ratio in LWE. It's going to be roughly sigma over Q. And combining, theorem 1 and theorem 2 gives you a full reduction from LWE to CLWE. And we also show how to apply our results for hardness, or to get more hardness results for learning mixtures of Gaussians. So the original paper defining CLWE shows that under quantum worst case hardness of lattice problems, you get hardness for learning roughly root n Gaussian components in your mixture. And why is there this root n here? This root n is here because BRST give the reduction from quantum, give the quantum reduction from worst case lattice problems to CLWE only for gamma being at least root n. And because gamma, as I said, is the number of Gaussian components in your mixture, they get stuck at this root n factor. We show under polynomial hardness of LWE how to bring this down to n to the epsilon for any positive epsilon. And if we want to stretch parameters a little bit, under a sub-exponential setting of LWE, we show how to get log of n to the 1 plus epsilon hardness for Gaussian component for learning Gaussian mixtures. So just to state what I mean here, I'm saying under this assumption in the middle column, there's no algorithm in polynomial time that can learn mixtures of Gaussians that can handle the following a number of Gaussian components in the mixture. So we went all the way from root n to log of n to 1 plus epsilon, but admittedly under quantitatively stronger assumptions, but assumptions that I imagine most of us probably believe.
The distinguisher type.
It is a distinguisher type, as well as, let me not get fully into it, but advantage and distinguisher type. Yeah, so right, yes, they do. So the main parameter here that allows us to get these flexible results is the fact that we play with this parameter gamma. So this gamma is going to roughly tell you the number of Gaussian components. And so the parameter gamma is going to tell you how spread out the Gaussians are and how wide each of the Gaussians are, because we also do play with the parameter. So yeah, they do look a little bit different, but they're all going to be Gaussian pancake distributions.
Sigma change.
Oh, is that the question?
Gaussian has a dense standard deviation, right?
Yeah.
They don't really.
Yeah, that's they
don't really change.
I mean, yeah, they change in scale, but they don't. The general structure is that you have Gaussian pancakes, but the quantitative, like how far apart they are from each other and how wide they are, does change.
So gamma is how far apart. There's mu and sigma, which is their.
Well, so mu is just the mean of the distribution. The means are going to be equally spaced out. They're going to be on the line generated by S, spaced out by roughly 1 over gamma. And the width, the covariance in the direction is going to be roughly beta over gamma. And so beta and gamma certainly change, so that the quantitative covariance matrix is going to change. That's true.
Becomes further apart, right? Gamma gets smaller, so they get further apart, which potentially becomes an even easier problem, but it doesn't. But it's still hard.
Exactly.
But beta stays fixed
No, beta changes as well.
and gets wider.
Yes.
Okay, so you're spreading out your pancakes more, but each pancake is back.
Yeah. Okay, so I mean, one can ask, this is a table of hardness. Like, what are the actual algorithms for this problem? This problem has really been studied a lot in statistics and machine learning. And so you can ask, okay, in polynomial time, how many Gaussian components can you learn in your mixture? And it turns out, there's been a lot of work on it, but still, the best algorithms that work in general can only handle a constant number of Gaussian components in polynomial time. So if you view things in a complexity theoretic perspective, you believe sub-exponential LWE, you can say, okay, there's this gap between constant and log of n to the 1 plus epsilon. Where's the true, what's the truth? How many Gaussian components can you truly learn in polynomial time? And this is an open question. You can also, oh yeah. So that's actually the direction I'm showing. Yeah. So this table is saying if you can solve Gaussian, you can solve density estimation for mixtures of Gaussians that can handle this many Gaussian components, then you can break polynomial or sub-exponential.
So these reductions tight enough that you can say something more concrete beyond polynomial time, like if you make an assumption about the best algorithm for continuous LWE, can you just give a complete overbound on that assumption?
Just to make sure I understand.
Yeah, like maybe you want to say that the best algorithm is the 2 to the gamma square algorithm for continuous LWE. Can you translate that to actual lower time, running time lower bound for learning mixtures of Gaussians?
I guess how does that differ from?
Yeah, because now you just say polynomial time, right? Versus non-polynomial time.
Oh, I see.
Like, so I'd like to get a concrete algorithmic hardness lower bound. And there's some appropriate assumptions for continuous LWE or for LWE, right? So because we have cryptanalysis of LWE, for example, that gives us actual concrete lower bound in how exponential the hardness of LWE is, and maybe we can translate those to learning.
I see. Yeah. I see. Yeah. I guess the question of does an algorithm for LWE imply an algorithm for this? I'm not so sure in terms of concrete.
Yeah,
That's not the question.
Oh, sorry. Yeah. How concrete so if you have a concrete statement of the reduction that is tight enough in terms of running time that allows you really to give a more fine-grained statement. So.
Yeah. I think I think that the reduction is reasonably tight in terms of there's some additive polynomial factors to me, but it shouldn't be too crazy. But yeah, I think it depends exactly what sort of fine-grained setting you care about. But yeah. Okay, so I mentioned the complexity theoretic way of interpreting the results. An algorithmic way to interpret the result is say, maybe even though these statistics problems have been studied for a long time, maybe you think there's some sub-exponential time algorithm for learning mixtures of Gaussians, specifically sub-exponential in the number of Gaussian components, G. If such an algorithm exists, that gives you a sub-exponential time algorithm for LWE. And certainly that would be a very striking consequence to, I assume, many of us in this room.
Specified how does the sample complexity and then reduction running time and these things translate?
Yeah, so it gets a little bit messy to quantify everything, but the running time is let me make sure. So certainly for the Gaussian mixtures, you have polynomial running time and polynomial sample complexity, and that gets you depending on the various settings, either sub-exponential or polynomial sample complexity for LWE.
So the sub-exponential LWE is a sub-exponential samples also.
Yes. So now let me give a sort of general overview of how we reduce LWE to CLWE. And I really claim, it's not a complicated proof. It's a relatively simple proof, and hopefully I can convince you of the reduction in the remaining time that we have. So the first step is going to be, as I said before, we're going to reduce a uniform secret over ZQ to the L, let's say in dimension L, to a binary secret S in dimension N, where N is a little bit bigger than L. And this uses existing secret key leakage resilience results for LWE. But actually, I'm going to make this reduction a little bit more general. I'm actually going to work with a k-sparse secrets S. And what do I mean? I mean sparse secrets where they're exactly k non-zero entries and they're plus or minus 1. So you could set k here to be n, and that's exactly binary secrets with a plus or minus 1 meaning binary here. And you might ask, what's the point of doing this? What's the gain? The point here is that the sparsity lets us claim that the norm of these secrets are exactly square root of k. And the point is we can tune this parameter k however we like to get you the L2 norm of the secret, however small you want it to be, as long as you preserve entropy effectively. And this sparsity is going to come up in a number of places in our reduction. One, it fixes the norm, but two, it uses the fact that the norm is small. And this gives you both like a small error blowup, but most crucially for our learning Gaussians result, the norm of the secret is going to become the number of Gaussian components roughly. So this is what lets us state hardness for a small number of Gaussian components. And when we do this is we adapt the existing hardness results for binary secrets and just adapt them to the k-sparse setting. Next, we're going to reduce discrete uniform samples to continuous uniform samples. And this is simple enough as adding noise to smooth out the samples. But there's a little bit of a nuance here that I'll get to shortly. And it turns out the blow up in the noise here in this reduction is going to be small because the L2 norm of the secrets is small. Next, we're going to convert these continuous uniform samples AI to continuous Gaussian AI. And might as well normalize things and divide by Q. And just to syntactically match with CLWE, we can make the unit vector, we can make the secret a unit vector and move the magnitude of the secret into gamma. And so that tells us that beta, we divide by Q to get roughly sigma over Q. And gamma is going to be the thing that takes all the norm from our secret, which we said was root k because of sparsity. So once again, using sparsity, we've gotten the fact that gamma can be as small as root k. Like in BRST, they show hardness for only root n gamma. Here we say, okay, we can get smaller by reducing k. And the way we show this is we take inspiration from BLMR, and we show a Gaussian pre-image sampling lemma that says, given something that's uniform mod 1, that's AI over Q, we can sample a pre-image A tilde I, such that the marginal distribution of A tilde I is going to be Gaussian, continuous Gaussian, and mod 1, it's going to be equivalent to the given AI over Q. It turns out that this lemma exactly allows you to reduce uniform samples mod Q to continuous Gaussian samples. And lastly, just to fully bring us back to the setting of CLWE, we effectively renormalize the secret distribution from k-sparse unit norm secrets to completely random unit vector secrets in Rn. And the way to do this is we apply a random rotation matrix to the samples. So for each AI, you just apply a random R times AI. And this has the effect of now making the secret R times S, where R is a random rotation. And because it's a random rotation, now R times S is going to be a uniformly random secret vector. Or sorry, uniformly random unit vector. So this is the full reduction, going from LWE to CLWE. And I'll talk a little bit in more detail about this second step, just as an example to get a flavor of sort of what's going on. So in the second step, we reduce a discrete uniform AI to a continuous uniform AI prime, let's say. How do we do this? I said we're just going to add Gaussian noise to all the samples. So think of alpha here as being small, like certainly less than Q. And what we're going to do, as I said, is we're going to add this Gaussian noise E tilde I to the samples. And now you can view this, this tuple in terms of the sample AI prime, which is the sum of AI and this Gaussian noise E tilde I. But this has the effect that we have to readjust our secret to somehow incorporate this added term we have to take care of. Or in other words, you can write the sample like this. You can write it in terms of a new sample AI prime, which is AI plus E tilde I mod Q. And this error AI prime has to be adjusted to handle the fact that we've changed from AI to AI prime. So first, we have to show that this AI prime, this distribution, is now continuous uniform, as opposed to given that AI is discrete uniform and E tilde I is a continuous Gaussian. And this holds by standard smoothing lemma techniques of Michaud and Regev. And now this step is a little bit more subtle, but even given this AI prime, we have to show that the conditional distribution on EI prime is going to be close to a Gaussian distribution. Indeed, this holds by standard convolution lemmas for discrete Gaussians. But the point here I want to point out is that the noise blow up here depends on the L2 norm of the secret. So once again, relying on the fact that the L2 norm of the secret is both fixed and small allows us to do this reduction without too much noise blow up. And this concludes the technical portion of the talk, and this concludes step 2. Just to move to some open questions.
Tightness of reductions, but really, it's really rather tight. I mean, there's really
yeah. So certainly between a fixed norm version of LWE and CLWE, we show pretty tight reductions between the two, up to some small thing we have a reduction from CLWE to LWE, but there's a small gap in that we can't show it all the way from complete unit vector secrets, the uniform unit vector secrets. We can only do it from some discrete set of secrets. But up to that, the reductions between the two are reasonably tight. Okay, so just to conclude with some open questions. One is, can we decrease the number of Gaussian components that we've shown hardness for? So I said it's hard for log of n to the 1 plus epsilon Gaussian components. Can you bring this all the way down to even constant, or a super constant, really? And ideally we'd like to show cryptographic hardness, but more generally, our lattices is really the right place to look to get these hardness results for learning mixtures of Gaussians. Another question is, can you build new or better cryptography from CLWE as opposed to LWE? And you might instantly complain and say, wait a minute, we've just shown a reduction from LWE to CLWE. So if you base any cryptography off CLWE, you might as well base it off LWE as well. But the point, that's technically true. But the point is, maybe CLWE gives you a different starting point with these distributions that allows you to think of something that you might not have thought of if you started directly from LWE. Lastly, I gave some examples of connections to other problems in high-dimensional statistics. Are there other natural connections? Are there other examples I could have added to this list? And certainly, I think the answer is yes. I think the question is just, what are they and what do these connections look like? Maybe an analogy with planted clique. With planted clique, there are lots of connections to other problems in high-dimensional statistics. Is the same true for CLWE? I don't know, but I think it's certainly an interesting question to look at. All right, thanks so much. That's all I had.
For example, show this picture of gases. You would do the reduction in specific this problem to the table directly to the, for example, mixture of gases. Or did you find that that's really a nice thing to have available?
Yeah, yeah, right. You can ask the question exactly as you said, can you reduce LWE directly to mixtures of Gaussians? Certainly, maybe. I do think CLWE is a completely reasonable middle ground, because what is CLWE really doing? It's really making the samples go from discrete uniform to Gaussian. And to get to mixtures of Gaussians, you have to go to Gaussian somehow. So that seems like a very natural way to do it. In terms of secret vector, secret directions, maybe the unit sphere isn't the right thing. I'm not sure, but
status that was like really just be able to see the definition as comes from this app.
Yeah, you're saying maybe the secret doesn't come from a unit sphere, maybe the norm is not fixed. can you show hardness for that? Maybe. Yeah, I don't know. It's a good question.
I think the relation between the product go beyond Q dictates how much like how many Gaussians. Again, it's dictated by the number of sequences. So it's not sure. I guess if I were to try to reduce from LWE to learning mixtures and Gaussians, I would go through these steps basically. And the question is, why not abstract it out? So you think it's useful? Yeah, it certainly comes across as aesthetically pleasing to us, right?
But yeah, do you have to go through this exact formulation of CLWE? Maybe not. Maybe there's some way to bypass this and press something.
Yeah, this arbitrary precision.
So I'm a bit confused by the problem itself. Like, so you have a reduction from CLWE to LWE.
Almost, but yeah.
But what is the model of computation you're considering? Because like on the one hand, you seem to be able to handle real, so I suppose that you want the real RAM. And on the other hand, you have the LWE prime, which is supposedly handled in the integer RAM model. So how do you like bridge between the two? Because like real RAM is infinitely more powerful than integer RAM. So how I mean, everything is, the reduction holds only in the real RAM model, I guess, and
So no. I mean, whenever we say continuous, really think about it as sort of, on a grid, essentially, not really continuous, but on a grid with arbitrary polynomial procession.
So you handle the continuous LWE as already discretized from the beginning?
Formally, yes. Formally, when you do the reductions.
But so in that case, if you're discretized over the torus, isn't it already a variant of LWE itself? So what is the difference between CLWE and, let's say, discretized CLWE at a fine-grained scale?
The distribution is different, first of all. Right. It's the distribution of A is sort of, rather than coming from Q, this comes from a Gaussian, right? So that's
okay.
That's a big difference, right?
Okay. So.
Actually, I find it would be useful to describe the scaled up version of CLWE.
So somehow,
discretize it and scale it up to the.
Somehow I think of sort of this discretization as a distraction, really. You have to deal with it when you write down a formal reduction. Really, it's so much cleaner to think about sort of just the continuous version. Mathematically, it's so much cleaner. Discretization is painful, and why do it? We want to live in a clean, useful world. Why do it?
Yeah, sure.
You have to do it to write a paper.
Yeah, but at one point you have to do it to go back to LWE, right?
To go back to LWE.
Yes. I mean, like even when you write, oh, it's interesting because we could build crypto on it, but at one point, if you just want to have a real crypto system, it will be discretized, so it will be.
That's right. That's right. So then you have to deal with these. Okay.
Well, I still find it would be useful to have a scaled up version.
I'm
just
sure
to describe those distributions in a larger domain.
I'm sure.
Yeah.
Do you think that, in the spirit of the previous question, do you think there are like other distributions that you could get equivalences between, like, okay, now you have one LWE distribution uniform over ZQ, you have another one which is this Gaussian distribution. Are there others?
Probably. I think another way to do a reduction is instead of going from discrete to uniform, like discrete uniform to continuous uniform, and then continuous uniform to continuous Gaussian, you could probably go to discrete Gaussian instead. Like discrete uniform to discrete Gaussian, and then discrete Gaussian to continuous Gaussian. That's probably a very other natural way to do it. In terms of things besides that, I think it'll be very interesting. Like sort of completely different looking distributions. But I mean, like, there's some worst case to average case reductions for like the secret distribution, for example, for LWE and also for CLWE. So you have to be a little bit careful, but certainly for the samples, I think it's an interesting question.
In this context, you have L infinity and L2. So the natural next thing to try is L1.
So as long as your distribution has enough entropy,
right?
It's not too weird. You should be
right. That's definitely true for S, and maybe it's also true for A somehow.
Right. It should be true.
Yeah.
So you're saying that the only constraint on the distribution of A should be the entropy? There is no geometry.
And niceness appropriately defined. So L infinity should L1 should work.
I see.
Yeah, I think like VLMR, for example, gives a whole list of distributions in a discrete setting. Essentially by like discrete image.
Just for the shortness, actually. For the Gaussian distribution.
All right, thanks everyone. Thanks to all the speakers for the fun workshop.